Right. So I guess from how the poll turned out, it was like actually even for the 2 dates. So I think to avoid confusion, I'm just going to keep the exam as the regular date as it's scheduled to not make it more confusing for everyone. So it will just be kept on the 21st, 22nd. The exam will be posted like 10 or 11 p.m. December 20th, and then you'll have around 48 hours to work on it, and then submit it by the end of the day, that or 11:59 on the day that the exam is normally scheduled. But again, I'll send out an email later and put an announcement to remind everyone. But it will be just on the regular day as stated in the schedule. Are there any questions on anything? All right. So this is the last result. I'm proving it shouldn't take too much longer, and then we'll just start going through some problems. But I do want to show this especially because it kind of connects to, for those of you who took another class with me, have seen kind of the more interesting result after this. But I'm just showing you kind of the development of where it comes from. So again, just a reminder, Mantel's theorem was avoiding complete graph on 3 vertices, giving us the maximum number of edges, which was a complete bipartite graph. And then Turon's theorem generalized and said if you're avoiding a clique of any size, of size r plus 1, then you can look at an r-partite graph, complete graph, where all the parts are equal, and that would give you the maximum number of edges. And so it's natural to avoid, instead of looking at a K3, you can interpret it as a cycle. So Mantel's theorem is telling us the maximum number of edges to avoid a 3 cycle. So then if you want to extend this, okay, what if I want to avoid a 3 cycle and a 4 cycle? How many edges can I place in the graph is the argument similar to the idea of Turon's theorem. So we will, maybe I shouldn't use the word recall after someone pointed out, maybe many of you actually haven't even seen the Cauchy-Schwarz inequality. So what it's saying here is just that if I take the dot product, this is the dot product squared, it's going to be less than or equal to taking the magnitudes or taking the dot product with itself for each of them and then multiplying them together. All right, so the proof is just a little slick way of approaching it, is just doing a counting argument. So I'm going to look at these pairs of vertices, and then I'm looking at, remember, the goal is I'm trying to maximize how many edges there are, right? We're proving that it can be at most this many edges. And so we said earlier that, well, there can't be anything distance 4 away because I would add more edges to it by making a cycle of length 5. So we know the best case scenario will be that they're distance 1, 2, or 3. And so by the uniqueness of distance, this would be looking at every possible pair of vertices, so that should sum up to n choose 2. All right, so unfortunately, not all these values are going to be simple to compute. But if we look at like C1, right? I'm looking at pairs, right? So this is braced as a set. There's no ordering of them. So what would the cardinality of C1 be? Equivalently, we're asking, right, how many pairs of vertices are there that are distance 1 apart? And remember, I'm not looking at an ordering here. So if I'm just looking at pairs of vertices of distance 1, 2 vertices are going to be distance 1 if there's an edge between them. And I'm not doing an ordering here. So if vertex 1 is adjacent to vertex 2, I'm not counting that as a different case as 2 adjacent to 1. So in other words, right, the cardinality of C1 is just going to be the number of edges. That's how many pairs there are of distance 1. So the cardinality for C2 is a bit trickier to kind of see how to do this. So if 2 vertices have distance 2 between them, right, like V1 and V2, what we're actually saying here is that, right, there's going to be one intermediate vertex between them to be distance 2. So sure, you can, if you read it like this, it does make sense to say that, but it still doesn't explain combinatorially how you would count this value, right? So if I look at these two vertices, I need an intermediate vertex, but there's something a little stronger that I can say besides that. Okay, there is an intermediate vertex, but then you can argue, well, there could be 10 million intermediate vertices. But that's actually not the case. We can only say there's going to be, like technically, I guess, at most one between any two. Because, right, if I had another intermediate vertex, this would form a C4, right? But I'm avoiding a C4. So therefore, this can't happen. So now it's still a little difficult to kind of see, well, how do I count all these cases of pairs, though, right? So if I'm going through and I'm looking at every possible pair with an intermediate vertex, it's actually easier to look at the intermediate vertex. I don't know if anyone sees it's not very, I guess, simple to visualize, but if anyone sees what would count the cardinality of C2, what would the value be? It's not like a simple answer of just like, 7 or something like that. But what are we trying to, how would we interpret by looking at W? I don't have to uniquely just look at just those two neighbors. In disguise, if I look at the degree of that vertex W, in a sense what you're treating as the intermediate vertex now, I can run through all these paths of length 2. So for vertex W, we should agree that by looking at that specific vertex W, by looking at the degree, which is 5 in this picture, I can choose any two of the vertices in the neighborhood, if I choose 2. Those would all be pairs of vertices of distance 2 that pass through the vertex W. But then I can do this with any possible vertex I want, right, as the intermediate vertex. So each time for any vertex with degree whatever, di, I'm going to see exactly di choose 2 number of pairs that have distance 2, right? So for this vertex W, there's going to be 5 choose 2 different pairs that I can pick, right? That is going to have W as the intermediate vertex. And the very important thing is you may say, yeah, you are counting pairs, but aren't you, that isn't going to be less than n choose 2 because you can count multiple pairs. But that's not going to happen, right? That's the importance of why we have this case of C4. I'm not going to count any pair more than once because of this argument. I would have a C4 if any pair got counted multiple times. So this does assure I'm counting distinct pairs. And then this is all the distinct pairs possible. Right? So it is, I agree in general without any like restriction that this value is generally not going to be less than or equal to n choose 2. Because you may repeat multiple pairs. But the key thing is if you repeat multiple pairs, then you'd be creating a C4, which is impossible. And then now, the question may look really difficult that, okay, how do I determine everything for distance 3 apart? Right? And right, so we're going to use the easiest possible argument here and just let it be 0. So now this is going to be a lower bound here. So now I'm just going to algebraically simplify this, and then we're going to see how this will be used later. So if you look at the form of what we have, we can actually simplify this pretty nicely. So remember, the summation is on this entire term here. So we should recognize what one of these things actually looks like is that this is actually summing over the degrees. So we see that this will actually simplify pretty nicely. So we're going to use that later. So now this argument is just now applying, we're just going to use the Cauchy-Schwarz inequality and then combine some inequalities together. So here I'm going to apply the Cauchy-Schwarz inequality, and I'm going to pick my the vector u to be the degrees vector, and then I'm going to pick v to be very boring. It's just going to be all ones. So therefore, replacing this left-hand side, so now, if you look on the right-hand side, right, we have the term that we used here in this argument. And also, this side, right, for the Cauchy-Schwarz inequality, this side is very simple. We can reduce this because this is the sum of the degrees, quantity squared. So the sum of the degrees is just 2 times the number of edges. And so now I'm going to apply the inequality up there, replacing it with that. And now we see, dividing out by 4 and taking the square root, we get the desired result. And so when you read this, you may say, okay, then isn't there going to be a pretty strong restriction on like the best possible case, right? In Turon's theorem, there was a unique graph for the Turon graph. And then now here, you're giving me a bound on the edges that involves a square root, which intuitively should probably put some constraint on what these best possible graphs can be. Because I guess for many integer values, right, this number would not be, this entire expression would not be an integer. And so understand that what I'm trying to do here is like understand the analog of Turon's theorem. Turon's theorem, we found the maximum number of edges avoiding a clique of size r plus 1, create the unique Turon graph. Now I'm trying to avoid a 3 and 4 cycle, obtain the max number of edges, and determine what is the most extreme case, right? As we said, this is like extremal combinatorics. I want now the most extreme case of, okay, just because you give me a bound, do I know it's actually good, right? So now let's look at the proof and see what the conditions are. When would I, where did I kind of cheat and avoid like equality of where it could have happened? So the first step, if you recognize here, is, well, I let this be 0. Remember, that's the diameter, the max distance. So if we said there's nothing of distance 3, and as we argued, there's nothing of distance 4 or more here to put the max number of edges. So I know one condition is that if equality does occur, everything would have to be distance 2, which puts a very strong structure on the graph. Right? Now you can basically draw it and just like draw kind of 2 layers below a vertex and then say, okay, this can't be too difficult since I only have 2 layers, everything's distance 2. So if we look at the Cauchy-Schwarz inequality, Cauchy-Schwarz is obtaining equality when what occurs? When the 2 vectors are scalar multiples. Equivalently, they're linearly dependent. So in our form, what is that saying? What is the constraining condition then in Cauchy-Schwarz under our argument here?
Regularity?
Exactly, right? Because you're saying that the all ones vector, right, should be a multiple, has to be a multiple, so it has to be all the same di. And so then it should also be clear that, as we said here, there's not going to be nothing of distance 4. So if I see any 4 vertices, or I should say, of, I guess, a path of length 4, no matter what, I better form a cycle, right? I better add in this extra edge. And so now, at least some of you who took 340 with me, this was like one of the last results we did in the class. And this is where it kind of all came from, right? So now you're saying, what graphs have diameter 2? Everything can be reached in 2 steps. It's a regular graph. Everything basically looks the same. I can look at a vertex and they all have the same number of edges coming out. And I know there has to be 5 cycle. It's the smallest cycle that I see because I'm avoiding a 3 and 4 cycle. I guess let me just start the page. And so the very surprising part is that it is sort of unsolved, but sort of not unsolved. So intuitively, maybe even by computer, you're thinking, this can't be too difficult since everything is just distance 2 away. You could maybe somehow try and brute force the constructions of what could happen, or maybe there's an infinite family of them. So the very interesting thing of this argument is that, as we saw, this proof wasn't very technical. It's Cauchy-Schwarz and just a little counting argument. The Huffman-Singleton theorem, you have to use the eigenvalues of the JC matrix to prove it. So it's a spectral graph theory using eigenvalues to prove this result, which is very interesting, like how you would restrict it to this. And the very strange thing is that this is just like necessary. So there may be a 57 regular graph that works. So the argument is very elegant. I mean, it's a somewhat long proof that some of you have seen that I've shown. But it's a very interesting thing is that these are the restricted values. And so the very strange thing of this semester of what happened is so just last month, there was a preprint of a paper. I don't think it's been fully accepted yet, but apparently someone claims that they've solved this case. So they actually proved a very general result and said as a corollary that this graph actually cannot exist. The very strange thing of all chances, even though I would say this is a pretty big result if someone solved this, is that the person that published this, or is, I guess, attempting to publish this, is putting into a Russian journal that isn't like a very known journal, which I'm surprised that it wouldn't be like a very popular journal in English. And so the preprint is completely in Russian, so I cannot read it. So I don't actually know if it's a validated proof or not. So at the moment, I think it's still being reviewed, and I hope someone translates it because I don't even know if it's true. But allegedly, it might have been finally solved. So it may actually not exist, but it was just last month that someone put up new preprint, but it's still under review, I believe, under the journal that it was submitted to. But it's very strange to me that it was just like a very niche Russian journal. It's not like a very, I guess, known journal in the mathematical field. So that's the, I guess, last thing I wanted to show. And I guess let me just mention one more thing. So on the 5 vertices, this is the 5 cycle. This should sound familiar. 3 regular graph on 10 vertices. This is the Peterson graph. These people named it after themselves, so it's called the Huffman-Singleton graph. And then, yeah, this was open for the last 60 years, but apparently maybe somebody just solved it last month. Any questions on that? Let me just write this for those of you.
Yeah. So I'm supposing we assume that the graph has a 5 cycle.
Mhm.
Where did we use that?
Use that. So, because otherwise we would find something of distance 4, right? Right. This is the key thing, is that if there are two vertices of distance 4, then it isn't the maximum number of edges in the graph, because I should have put an edge here. So remember that the goal of this argument is that I'm trying to make the graph be as dense as possible. I want to pack as many edges in there. But if there's anything of distance 4, I should have put an edge between the two vertices. Otherwise, this is not maximum avoiding a 3 or 4 cycle. Is that
Right. So if there's anything distance 4, we need an edge, creating C5. So I guess this is why there's no pairs of distance 4, and we can like look at pairs of distance 1, 2, and 3. Why does this say the small cycle is a C5?
wait? Say that again.
Does this say why the small cycle is a C5?
So, I guess if you may have to put the extra, yeah, maybe I do have to kind of say that. I would say that I guess your assumption should be a little stronger, that you're assuming there's at least 5 vertices in this graph. If there's at least 5 vertices, we should agree that I guess you can just look at it in the simple manner that if I had a tree on 5 vertices, or sorry, I should just say specifically if I had the path on 4 vertices, right? That's what the point is, that once you have at least 5 vertices, either you better have an edge between these two vertices to create the 5 cycle, or you would have 2 vertices of distance 4. Or I'm not sure what, I guess, you're doubting or uncertain about.
Yeah. I think I'll just ponder it for a while.
Okay. Yeah, I mean, I guess regardless, maybe the better way to look at it also is to maybe think about it more, not worrying about this, that you could just look at this condition. I mean, if you look back at the proof that we did 2 years ago, you'll see the importance of why you need this, or why you do assume that it's growth 5 in the proof. So maybe that is a better way to think about it, is that I guess it isn't fully cleanly like explained by an inequality on the step, but if you do want to bound it by this, I'm pretty sure in the argument you need the 5 cycle argument. I'm pretty sure. Actually, I guess you don't. Yeah, I'll try and, I guess, we can talk about it later. I'll try and think of another way to explain it a little more clearly.
That's good.
Are there any questions on that? All right, so that's, I would say, all the material we'll cover for the class, but yeah, the last few sections are just kind of showing you some things on what you call extremal combinatorics. It's just like putting some conditions on some problem graphs or whatever, and then with that condition, like looking at extremal condition like values, like how good of a result can you get under that specific condition. And we saw like Turing's theorem was a unique form of putting the restriction, avoiding a click. But once you avoid a 3 or 4 cycle, this problem becomes very difficult. And so as you can imagine, if you try and generalize this more over more cycles, right, there are no like perfect results. Because even for these 2 cycles, it's not even exactly known maybe until today. But like, for example, if they want to avoid like all even cycles up to a certain value, there are like asymptotics and stuff like that, but there's no known exact values that will bound the number of edges restricted, given the restriction that you can't have certain cycles inside the graph. So you can see that just tweaking the problem a little already makes it a lot more difficult. So it's very unfortunate I didn't get to go through like the details of this chromatic polynomial, but the nice thing is we can actually see a proof of this going back to counting, which is using inclusion exclusion. So this concept of chromatic polynomial is giving a counting technique or method of thinking about coloring a graph. And now you can see how kind of 2 different things are going to connect together. There's a lot of interesting properties behind this polynomial, but I more want to show, I guess, the combinatorial side of it than the graph theory side of it. So as a simple example, if you have this path of length 2, so understand that I'm doing this in a labeling. So if I look at this vertex first, so understand I'm not looking at chromatic number to minimize. I'm just saying, give me 6,000 colors. Then this vertex clearly has 6,000 choices, or Z choices. Whatever color is used here, this obviously now has Z minus 1. And then finally, for this one, it can't use the same colors too, so there's going to be Z minus 1. So it's kind of a strange way to look at it, because combinatorially with a numerical value, right, you would say there are 732 number of colorings using, I don't know, 10 colors or something like that. But instead of reading it like that, I'm going to read this as a function, right? So it's actually P of G Z, so it's a polynomial in terms of the number of coloring Z. So you may say for a small graph, yeah, sure, there's a way I can determine what the total number of colorings is or what the polynomial is. But you could imagine if you give me a large arbitrary graph, this problem is very difficult. There are techniques using recursion where you can kind of work backwards and recover back, like the smaller graph, because if you get to something here, then of course I can just brute force and understand how many there are. And there are recursive formulas that work like that. We're going to prove this, though, using inclusion exclusion to find a formula for this chromatic polynomial. So what I'm saying is that when I look at the subset of edges, I may just have one edge, but I'm not saying let's ignore all the other vertices. So it's still induced on like all the n vertices in the graph, but I'm only going to visualize it as seeing one edge, while everything would be just a bunch of isolated vertices. So of course, this already looks like the sort of like inclusion exclusion. So if we look at this form, right, what we're saying here is that this is e to the third number of components. This is e squared. There's two components and one component. Right, so now we want to apply inclusion and exclusion. I mean, the form looks relatively simple to this, but it's still, of course, the most difficult step of all, always when you're applying inclusion and exclusion is clarifying what the sets are. Does anyone have a guess? How would I define these subsets, capital A, in a, I guess, smart way, so that when I look at the complements, so remember at the end, right, the thing I probably want to conclude at the end or get to this form, right, this part should be corresponding to what I'm looking for here. So from this notation, it might be slightly deceiving since I wrote n. Understand this side, I'm running through the edges. So I want to define these sets to be the colorings such that I'm doing, so understand, I'm coloring the vertices, right? This is standard chromatic number on the vertices, but I'm interpreting how to do it on an edge. So the key thing I want is going to be this representation, right? Intersecting the complements. So in other words, right, this is like the, as we say, as I call it, like the sieve method, right? Well, what do I want to, what are the things I don't want? At the end, I'm looking for the sort of proper colorings with the Z colors on the graph on the vertices. So what am I trying to remove? What I need to get rid of should be the forms, right, where they're improperly colored. That's what I need to get rid of. So in a sense, you're looking at when it's colored incorrectly. So this is very simple then, right? Because if an edge is colored incorrectly, we're actually saying that the two endpoints are the same color. That's how it would be improperly colored. So now think about it, right? If I take the complement, right, we're looking for a coloring of G, where that edge now has different colors. So you're saying the first edge, I want different colors. Well, now what am I doing by inclusion and exclusion? Let me now look at the second edge. I better make sure those two are different colors. And I want the next edge to be different colors. And the next edge, etc. They all better be satisfying the condition that when I look at any edge, the two endpoints are different colors. But that's exactly referring to a proper coloring of G. Oops. And so we're making our life easier, right? We're going to count this in the other way where they're bad colorings. And now you can pretty much see, just because I gave you the answer first, is that, well, how does this work by counting it with respect to the A's instead of the complements? So if I just use some of the edges, right? Well, then this is pretty simple, because if I use a few of the edges, and I'm counting this, or I guess maybe you should look at it as like A sub, I don't know, 1, 2, 2, 3, and maybe like 4, 5. How many colorings are there such that the two endpoints of 1, 2 are the same color, and 2, 3 are the same color, and 4, 5 are the same color? But then what are we saying? Well, if you told me 1, 2 has to be the same color, and then 2, 3 has to be the same color, this entire component must all have the same color. Every vertex must have the same color. Well, then how many choices are there for the color? this component has Z choices. Then this isolated vertex, obviously I can choose Z different colors, this one Z different colors. Now I want this component, this edge, to also have the same color for the endpoints. So this entire component also has Z colors. And hence, the total colorings for this specific case will be exactly Z raised to the number of components. And that's how you get the right answer. Are there any questions on that? So it's a very interesting way that even though the setup for the polynomial looks really messy by what was written, but it actually provides some way to actually, I guess, count the number of couplings using an inclusion and exclusion argument. So let me just write down one more problem here, and we'll go through it on Monday, or you can also just think about this yourself. So for simplicity here, I'm assuming that you can't have three different lines that are going to meet at the same point. But what you're picturing here is you just have these points here, and then I'm going to always draw a line or chord right between any two of them. So even here, I'm drawing it like that. All right, so I'll stop here if you want to think about this. Interesting thing of what you can do on the second part is you can actually turn the question into imagining this now as a planar graph instead. The first part is just a purely combinatorial question, but you can do a slick argument using planarity on Euler's identity, but you do have to apply to, technically this will be a multi-graph, but it still holds. But you can think about how you can try and use Euler's identity on this to count the total number of faces or regions inside here. But just be aware this graph will be multi-graph, just because when you form this edge here, there's technically another region will be formed because you have the circle that's forming an edge also. So this would be a multi-graph by this construction. Are there any questions on that? All right, so I'll stop there. So we'll just go through some more problems on Monday.